In section 1.5, we'll be talking about limit-based continuity. So continuity means that there are no interruptions in the graph. A simpler way to put this maybe is that if a graph is continuous, I could draw the entire graph, like trace over it, without lifting up my pencil. So there are a few specific types of discontinuities that we're going to talk about. The first one is where f of c is undefined. And so on the graph, this might look like a hole. So we have a special name for that that's called a removable discontinuity. For number 2, another place where you would have a discontinuity is where the limit does not exist. So when you notice that the left limit does not match the right limit, this is called a jump discontinuity. Number 3, again, the limit doesn't exist, but the reason why is a little bit different. You might notice that the limit is going to positive infinity or negative infinity, either on the left or the right side or both. That is called an infinite discontinuity. And number 4, when the limit itself doesn't actually match up with the function value. So you can see here, my limit exists because the left and the right sides match up, but I just have this other point here that doesn't fill in. That's another example of a removable discontinuity. So discontinuities are removable if the limit exists, but it either the function is undefined or doesn't match the function definition. And we call it removable because if I were to move this point up here instead, then it went away. My graph would actually be continuous. I can see that here in the first example as well. If I were to fill in that circle, then my graph would be continuous. For the examples number 2 and 3, the jump and infinite, we call those are both non-removable. So I would not be able to just fill in one single point and then make that graph actually continuous. Now let's give a more precise mathematical definition for what it means for a function to be continuous. So we will say a function f is continuous at x equals c if, number 1, f of c is defined. So that means when I evaluate the function at c, I get a number. Number 2, the limit as x approaches c of f of x exists. Which notice that by saying that, that means that the left and right limits exist as well, and they match up. And the third thing is that number 1 and number 2 have to match. So I'm going to say the limit as x approaches c of f of x is equal to f of c. So whatever I get for my limit, I also get for my function value. So all 3 of those things have to be true in order for a function to be continuous. If one of them is false, then automatically the function is not continuous. In example 1, we will decide in these graphs if the function is continuous at the given value of c, so the place marked on the graph, and if it's not, we're going to determine which of those 3 rules of continuity the function fails. So remember, number 1, the function has to be defined, number 2, the limit exists, and number 3, those 2 things match up. We're also going to add another layer here, and we're going to classify as removable, jump, or infinite discontinuities if we have them. So on some of these graphs, you might be able to tell just quick visual, like with the very English definition, that there's a break in the graph, that you know it's not continuous, but we have to make sure that we actually give a mathematical reason. So in A, we're looking at 1, and we can see there's a break in this graph. So I can say, no, this graph is not continuous. The reason why is that the limit does not exist. The left and the right sides do not match up. So the limit as x approaches 1 of f of x does not exist. Now, if I check number 1, this function is defined. I see that the point is filled in, but I can tell the limit does not exist. When that happens, when the left and right limits don't match, we call this a jump discontinuity. Part B. So the first thing I want to check, is my function defined? It's not. I don't have an f of 1. And so automatically this function is not continuous. I don't even need to check. I do see that the limit exists, but f of 1 is undefined. This is an example of a removable discontinuity. It might also be called a point discontinuity. Number 3, I'm looking at, or part C, I'm looking at 0. And so that's this point up here. The function is defined. The limit exists. The left and right sides match up. And it matches up with that point value. So yes, this function is continuous. You can see there I could draw the whole graph just with one swoop of my pencil. I wouldn't have to pick it up at all. Part D, I'm also looking at 0, so I can see my function is defined. My left and my right sides match up, and it matches the function value. Again, that is continuous. Part E, I'm looking at 2. I see there's a vertical asymptote here, and so I can see that f of 2 is undefined. So automatically this is not continuous. I could also say the limit as x approaches 2 of f of x does not exist. That would be another reason. Either one of those would be okay in this case. Remember that if a function is approaching infinity or negative infinity, that the limit does not exist. When we have vertical asymptotes, we call them infinite discontinuities. Part F, we have another vertical asymptote. And so again, I could say my limit is equal to infinity. Both sides match up at positive infinity, but either way, my limit still does not exist. My function is defined though. I just have a single point there. So my only explanation that I could really give here is that the limit as x approaches 2 of f of x does not exist. So that's a no. We'll still call this an infinite discontinuity since the limit is infinity. All right, part G. You might notice this hole over here, but what this problem is actually asking you for is this function continuous at -2? So be careful here. Just because a function is discontinuous somewhere doesn't mean it's discontinuous everywhere. So this function at -2, I can see my limit exists, my function's defined, and they match, so that is continuous. Part H, my function is defined, I see a point. However, the left and the right sides don't match up. And so, no, this graph is not continuous. I would say the limit as x approaches -1 of f of x does not exist. And this is kind of a mix between a jump and an infinite discontinuity. You could call it either one or an infinite jump. But either way, those are both discontinuous. In our last section, we saw that some limits we could find by just evaluating at a certain x value, and those were functions that were continuous at those x values. It was where we had discontinuities that we needed to do something else with the function, like factor and cancel. So here's a list of functions that are continuous over their domains. So all polynomials are continuous. Rational functions are continuous over their domains, so everywhere besides where they have vertical asymptotes and holes. Root functions, trig functions, except again vertical asymptotes. Sine and cosine are continuous everywhere. That's going to be important for us in calculus. Inverse trig functions, especially arctan or inverse tan. Exponential functions are continuous everywhere, and logarithmic functions are continuous on their domains. So let's take a look now at a function g of x. We can look and see this graph has multiple discontinuities. We're going to analyze at certain points. So for example, number 1, we'll do x equals -8, and we'll decide if it's continuous or not, and we'll use that 3-part definition of continuity. So one thing I want you to notice is that this function is called g of x. So we want to make sure that we're always using g of x when we're in our explanations. It's easy to just use f of x like normal, but we would get points taken off on the AP test. So the first thing we want to check is g of -8 defined? And so when I look at my graph, I'm looking for a point. So g of -8 I see is 4. That is defined, so I'm good to move on. If it weren't, I could just stop right there. The next thing I want to do is find the limit as x approaches -8 of g of x. And so remember, if I'm finding, sorry, I wrote infinity, I meant an 8. Remember that in order for that limit to exist, the left and the right sides have to match up. So when I'm looking at -8, I see the left side is approaching -5, the right side is also approaching -5, so this answer is -5. So my limit exists. I'm good to go. The third thing I want to check is, were my answers for number 1 and number 2 the same? So number 1, I got g of -8 was 4. Number 2, my limit was -5. Those do not match. So I'm going to say the limit as x approaches -8 of g of x does not equal, I'm sorry that I keep writing infinity, -8, does not equal g of -8. And so that automatically means my function is not continuous. So I'm going to say, therefore, remember that's a symbol, a triangle symbol with 3 dots, g of x is not continuous at x equals -8. We also want to classify this discontinuity. So when my limit exists, but my function value doesn't match with it, that is a removable discontinuity. Again, that would mean I could fill in this point here, and then my graph would actually be continuous if I took that point and moved it down. So I would remove the discontinuity. All right, let's check at -6. So I see on my graph -6 is right here. So g of -6, first thing I want to check, g of -6 is -7. Good to go. Number 2, for the limit, I'm checking the left and the right sides. Those both approach -7 as well. So the limit as x approaches -6 of g of x is equal to -7. That checks out. The third thing I'm checking, did I get the same answer for number 1 and number 2? I did. So I can say, therefore, g of x is continuous at x equals -6. All right, I want you to pause the video now and see if you can try number 3 on your own. Okay, so again, you can probably tell by looking at -4 on the graph that this graph is not continuous. I can see it's not actually connected there. But let's write out our definition for y. So number 1, I'm checking g of -4. That means I'm looking for the filled in point. That is -5. That's good. Now number 2, I'm checking the limit as x approaches -4. I can tell by looking at the graph that the left and right limits are not the same, but let's actually write that out. Limit as x approaches -4 from the left of g of x, that's equal to -5. I can see here that's approaching -5. The limit as x approaches -4 from the right of g of x is -2. You can see that here. Those don't match, so I can say, therefore, the limit as x approaches -4 without a direction of g of x does not exist. Now that wasn't what the question was asking me. It was asking me, is this function continuous? Automatically, if that limit doesn't exist, I can say, therefore, g of x is not continuous at x equals -4. So then let's classify that discontinuity. You might be able to tell from the graph, but also when my left limit and my right limit don't match up, but they're both finite numbers, then I call this a jump discontinuity. If one of them was infinite instead, then I would call it an infinite discontinuity. So this one is a jump because my graph jumps from one piece up to another.